Alright, so I am Matthew Colwell and I will be doing a biomechanical analysis on the football kick with the goal of maximizing horizontal velocity. The purpose of this analysis is to examine the biomechanical principles underpinning an in-step football kick with the overall goal of maximizing horizontal velocity. Achieving this requires applying an optimal impulse, that is, maximizing the product of force and contact time at the moment of impact. To do so effectively, the performer must coordinate a sequence of movements across multiple joints and planes, producing an efficient proximal to distal kinetic chain. Each phase of the kick contributes uniquely to the generation and transfer of energy from the trunk and the thigh through to the foot and ultimately to the ball. This movement can be divided into four key phases: the approach and plant, the backswing, forward swing, and the follow-through or recovery. Each phase contains critical features that collectively determine how efficiently force is produced and transferred. During the approach and plant, the focus is on establishing a stable base and positioning the body to generate forward movement. Literature indicates that elite players adopt a controlled yet dynamic approach, optimizing stride length and trunk alignment to facilitate energy transfer through the supporting leg. Hip extension and contralateral trunk rotation prepare the body for rapid hip flexion that follows. The support leg absorbs impact forces and redirects them efficiently through the pelvis and thigh, which is a finding supported by Inoue et al. In 2014, who noted that the stability and angular stiffness of the support leg are strong predictors of overall kick velocity. In the backswing phase, the kicking leg undergoes hip extension and knee flexion while the pelvis and trunk rotate away from the ball to store elastic energy. This proximal motion is critical for developing angular velocity, setting the foundation for rapid acceleration during the forward swing, which is the next phase. According to Lees et al. In 2010 and Nunome et al. In 2006, a lot of skilled players displayed coordinated segmental timing, where peak hip extension velocity precedes knee flexion velocity. Ensuring energy transfer follows the proximal to distal pattern, essential for maximal speed at impact. Next up is the forward swing. The emphasis shifts from coordinated hip flexion, knee extension. Sorry, the emphasis shifts to coordinated hip extension, hip flexion, knee extension, and ankle plantar flexion. These movements occur in a tightly sequenced chain that accelerates the foot forward towards the ball. Studies by Shan and Westerhoff in 2005 and Kellis and Caddis in 2007 highlight that efficient angular momentum transfer combined with trunk and pelvic rotation directly correlate with foot velocity at impact of the ball. Also, ankle plantar flexion creates rigidity in the distal segment, improving efficiency of force transmission into the ball. Peacock and Ball in 2018 described that a firm locked joint angle at impact increases both impact efficiency and resultant ball velocity as energy losses from joint compliance are minimized. After impact, we have the follow-through phase, which allows for safe dissipation of residual momentum. In this phase, there is continued hip flexion, trunk rotation, and gradual deceleration of the limb, preventing abrupt loading, while also contributing to accuracy and control. Lees et al. In 2010 emphasized that a smooth follow-through ensures energy is channeled into the ball rather than absorbed prematurely by the limb segments. So, in constructing the deterministic model, several quantitative and qualitative variables emerge as key contributors to ball velocity. These include hip and knee angular velocities, ankle plantar flexion velocity, degree of trunk rotation throughout the phases, mass and velocity of the striking foot. The sequence and timing of these variables dictate how effectively impulse is applied. An effective kinetic chain ensures that momentum/energy flows seamlessly from the trunk to the foot, maximizing velocity at the point of contact. So when recording the skill, according to literature, to record it effectively, the camera should be set up between 8 to 10 meters away at subject hip height, while having a high frame rate camera positioned at about 90 degrees in the sagittal plane. Lighting included consistent lighting profiles across the body with bright, even strobe lights for high capture frame rates, minimal or tight, non-reflective and dark clothing to highlight joint markers and their visibility. object for video calibration, so whether it be a 1 meter stick or another arbitrary object, and clear and effective preparation and instruction on subjects' required movements. So for this analysis, the performance was recorded with these previous considerations in mind. It was captured at 120 frames per second, approximately 4 meters away, allowing for precise analysis. The lighting and clothing were selected to enhance marker visibility rather, and we used a 1 meter ruler for calibration. We had dark clothes on, tucked in the shirt, just to kind of highlight the joint marker visibility. These methods align with the recommendations of previous literature, which had a strong emphasis on consistent lighting and appropriate camera distance, sort of thing. So next up are the critical features. Through qualitative analysis, 2 critical performance variables were identified: hip flexion timing and ankle plantar flexion rigidity. On the first slide here, we have hip flexion relative to the trunk and knee. We can see the change in hip flexion across the photos, and we can see that in terms of sequencing in hip flexion, the hip flexion precedes that of the knee extension. With these photos, we can also see that the hip position relative to the trunk and the rotation about the trunk is very clearly quite minimal, with the hip marker really only being behind the trunk slightly in the beginning and slightly in front upon impact. The photos beneath kind of illustrate this. Next, we have ankle plantar flexion in relation to the tibia. We can see here that the ankle joint is in slight plantar flexion approaching the ball, and it maintains this up until impact, where it is significantly noticeable the degree of dorsiflexion and the change of angle, rather the change of foot position. After impact, however, it returns into a natural dorsiflex position, as is illustrated by the photos. Moving on to our quantitative variables, we have knee extension velocity. We used Canovia's goniometer and stopwatch feature, and I was able to determine that in the forward swing phase of the subject extended their knee by 48.6 degrees in 0.091 seconds, giving us an angular velocity of extension in the knee of 534.06 degrees per second, or in radians, 9.321 radians per second. The photos here illustrate that, with the frames being the start and finish of the stopwatch. Second quantitative variable is knee flexion. Knee flexion velocity during the backswing phase, similar to the previous variable, using Canovia's goniometer and stopwatch feature, calculated that from the moment of toe off, the subject then underwent 103.8 degrees of knee flexion in 0.408 seconds. This ends up giving us an average knee flexion velocity of 86.1 degrees per second, or 1.424 radians per second. Photos once again photos show the points of littlest and greatest flexion in the backswing. So, quantitatively, the knee flexion and extension velocities were both below those reported for elite players, according to literature. We see in the table here, Kellis and Caddis in 2004 and Shannon Westeroff both identified that higher knee extension angular velocities directly correspond with increased foot velocity and ball speed. In the observed performance, insufficient knee flexion during the backswing reduced the available range of motion, thus limiting extension velocity. The observed hip flexion was also delayed relative to elite models, suggesting that suboptimal sequencing between the hip and knee extension was present. As noted by Lees et al. In 2010, elite performers initiate hip flexion early in the forward swing, creating a smooth transition that enhances energy transfer to the distal segments. In this case, delayed activation limited knee extension velocity and consequently reduced foot speed at impact. Similarly, the ankle plantar flexion exhibited reduced rigidity during the final swing phase. Studies by Peacock and Ball in 2018 and Tamara et al. In 2023 show that a rigid plantar flexed ankle joint upon impact is vital to efficient energy transfer. The delayed plantar flexion in this performance will likely resulted in energy absorption at the ankle rather than an effective transmission to the ball, and this reduced impact efficiency. Based on these findings, several evidence-based corrections can be proposed. To enhance ankle rigidity, targeting strengthening of the plantar flexion muscles and plyometric exercises could increase stiffness and control during high-speed movements. Implementing video feedback would also assist in refining the timing of plantar flexion before impact. For improving knee flexion and extension dynamics, plyometric quadricep training combined with tempo-based kicking drills could also develop more explosive angular velocities. Finally, hip flexion timing may involve strengthening the hip extensors to improve the stretch shortening cycle and enhance reactive acceleration during the forward swing. These recommendations are supported by the findings of Kellis and Caddis in 2007, Lees et al. In 2010, and Nunome et al. In 2006, who each link segmental strength and timing to improve kinetic chain efficiency and ball velocity. In conclusion, the intercept football kick exemplifies a highly coordinated, multi-joint movement governed by the principles of impulse, velocity, and efficient energy transfer. Through both qualitative and quantitative biomechanical analysis, the performers demonstrated clear deviations from elite standards, with ankle rigidity, hip flexion timing, and knee joint angular velocities all being subpar. However, by applying biomechanical reasoning to detect these faults and implementing targeted corrections, the performer can significantly enhance their performance, ultimately better achieving the task goal of increasing horizontal ball velocity. Thank you for listening to my biomechanical analysis.